Okay, here we go. If you have any questions, remember, send me an email. I've got the calendar set up. So we started yesterday, last class on Wednesday. So this is like the next 3 weeks. So we got all the way up to 11.8. The school's taking Monday off, so I won't give you a class on Monday. And once again, I'll be giving you one of these classes a day. Make sure you're doing your homework and then send me a picture of your homework via email, my email, and I'll give you credit for it. When we get to the algebra review, I'll give you a practice test. You'll study the practice test. I'll give you ample time to ask questions if necessary, and then I will send you a copy of the test to finish at home, and you just simply need to take some pictures of the pages that you do and send those in to me. So here we go, homework for 11.2. As always, remember this is a video, so not necessarily I'm going to talk faster, but remember you can always pause. My assumption is I'm not going to do the normal pause that we would do in class for kids to write something down. I'm just going to continue. So make good use of the pause button. All right, here we go. So we're going to get three shapes today: a parallelogram, triangle, and rhombus. And we will get formulas for each one. Remember, chapter 11 deals with area. Chapter 12 will be doing the volume surface area of three-dimensional shapes. But chapter 11 is all just plain figures, flat shapes. Oh, couple theorems today, one for each shape. All right, tough day. Remember, we gotta prove things. So, do you remember when we years ago when we first encountered a parallelogram? You were probably told by your teacher when you calculated the area that it was just simply base times height. They simply threw that fact out for a parallelogram, but they never proved it to you. Today, we'll prove it. All right, so we're going to start off by remembering for a parallelogram, any one of the four sides can be the base. I'll just choose the bottom. And the perpendicular distance between the base and its opposite side, we call the height. And in sixth grade, you were told area of parallelogram is base times height. Great, and that is true. We just have to prove it this year. So let's prove it real quick. All right, so you're given the shape and its parallelogram, and you're supposed to prove that the area is base times height. Well, I just got a parallelogram there. I have no information whatsoever, so we better do something to get some information. So the first thing I'm going to do is I'm going to make a couple perpendiculars. So I'm going to drop a line straight down from point P to segment SR. I'm going to make it perpendicular. And then I'm going to drop a similar line from Q. So it's going to be the same distance. How do I know it's the same distance? Because it's a parallelogram. So PQ and SR are parallel to each other. Therefore, if I drop any perpendicular down from segment PQ to segment SR, they will have equal distances. So I've made two triangles there. Well, let's see. So the statement I just made there that any perpendicular will be congruent to any other perpendicular on a parallelogram. So that would mean that PV, that was that perpendicular we just dropped down, is congruent to QT. And further, then that means that PQTV is a rectangle. Now I'm leaving a little bit of detail off there. Remember yesterday we defined a rectangle as has a quadrilateral with four right angles. So, well, there's two of them listed right there, but because it's a parallelogram, then we know that any two interior angles of a parallelogram, any two consecutive ones, are supplementary. They add up to 180. So if one's 90, then the other one has to be 90 as well, too. And that's, therefore, we have all four angles right there. Angle P, angle Q, angle T, and angle V there will all be 90 degrees. Therefore, it's also a rectangle by the definition. Okay, cool. So I just marked right there that those two segments there are equal or congruent. I'm also going to further claim that PS and QR, look at where PS and QR, well, they have to be because those are opposite sides of a parallelogram. So those are also congruent. And now if you look at those two triangles that I just made, they're right triangles. And I just showed you that one leg and the hypotenuse is congruent. So therefore, the two triangles are congruent because of hypotenuse leg. If the two triangles are congruent, okay, watch what I'm going to do. Find the shape PQRS. So PQRS, that is the parallelogram. We'll see, that would be equal to, watch the shape, PQRV. That's part of it. Then I need to add that triangle there on the left, okay? That's pi split 19. Remember, I can take any shape and break it up into smaller parts. I'm going to do the same thing, just on the other side. So I'm going to go to PQTV. That's the rectangle itself. Excuse me. The rectangle is made up of PQRV. Hey, look, that's the same thing I just said above. Plus now the triangle on the right. Once again, that's a postulate 19. Now, look at those two statements. Both of those statements have a PQRV in there. So I'm going to say the following. I'm going to say that PQRS, trace it out with your fingers if you need to, PQRS must be equal to PQTV. Now, how can I, PQRS is equal to those two values right there? Well, how can I say that? Well, look at the two statements above it. So the two statements above it says PQRS is equal to PQRV plus PSV. Now I'm gonna have to pull up my marker here. This will be easier to do in class, but I'll manage. There's my marker. Here it is. Okay. So let's see. No, I want this. So this statement right here, that the two triangles are congruent, and this statement right here that PS is equal to Q. I'm use both those statements. So if the two triangles are congruent, then that means that I can write either one of those right here. I can do a substitution. So what am I saying? I'm taking, I got too many colors here. Let me erase that, clear all drawings. So I'm going to take this statement right here, PQRS. I'm going to rewrite it right here. This part of it says PQRV plus PSV. This statement says right here that PQRV plus QTR, and we said right here that PSV is congruent to QTR. So this part right here, I can do a quick substitution. And if that's true, then that means that PQRS is equal to PQTV. Hopefully that made sense. Okay. Remember, that's just a quick substitution. So why is that important? Well, now I have two different shapes that are equal to each other. PQTV is a rectangle, and the area of a rectangle is PQTV. And since I made the statement there, the third one from the bottom, that PQRS is equal to PQTV, and PQTV is equal to base times height, then so is PQRS. And that's how the proof ends. And once again, I said this in the last class, this is why your sixth grade teacher didn't prove this to you, because it's a challenging one to prove. But we just proved it, and this is our first theorem. So it's the area of parallelogram is base times height. Great. I'm telling you something that we already knew. Two of the shapes we already know for today's class, and one of them we don't know. It's a new one. But this one's pretty straightforward. All right, pause the video if you need to write this down. There are some words here as well, too. Just remember the base could be any one of the four sides, but as soon as you name the base, then the height must be the perpendicular distance between the base and the opposite side. Okay, so it sounds easy, and it is. This is more like a sixth grade or an eighth grade example right here, where they give you the base, they give you the height, you multiply the two numbers together, you get 10 square feet. You know, that's what it looks like from sixth to eighth grade. In geometry, we're just going to make the problem more challenging. So recall special right triangles. We have two of them. We've got a 45, 45, 90 special right triangle where the two legs are equal to A, and the hypotenuse is equal to A root 2. And then we have the other one, which is a 30, 60, 90, where the short leg, the side opposite 30 degrees, is A, the long leg is A root 3, and the hypotenuse is double A. We're going to use that information right there. You might want to write it on a piece of paper, keep it off to the side to this problem. Okay, so here's your geometry example of area of a parallelogram. Yeah, the formula is still base times height, but look, we got the base of 10, but we don't have the height. The height is missing. If I had two sides of that little triangle right there, I could use Pythagorean theorem, but I don't. I only have one side, but look at that angle, it's 45. So if it's 45, then that means it's a special right triangle, right? Remember, this is our special right triangle where the leg is equal to A. It's labeled H here in our example. And the hypotenuse is equal to A root 2. So on our particular shape, the hypotenuse is the value 8. So I can set 8 equal to, I'm just substituting an H for A here, to that. Now I can solve for the height because I need the height there to solve our area problem. So all I'm going to do is divide both sides by root 2. Can't have a square root in the bottom. So we multiply top and bottom by the square root of 2. So we get 8 root 2 over 2, which reduces to 4 root 2. So that's my height. It's not pretty, but I throw that into the h value there, multiply by 10. So I get 40 root 2. There's no units listed right there. So we simply put the word square units. So there's a geometry problem involving parallelograms. It's much more challenging than a 6th or 8th grade parallelogram problem. There's a couple of those for homework. All right, why so difficult? Well, you're not in 8th grade. The world's more difficult. Real life is challenging. All right, let's move on to triangles. Now, we've learned from a long time ago that area of a triangle is 1/2 base times height, or base times height divided by 2. And notice that's what this proof is saying. We got a triangle, XYZ, or XZY, and it says prove that the area of that triangle is equal to 1/2 times YZ, that's the bottom, we'll call that the base, times H, and that's the height. So that's my proof. All right. Once again, this is a pretty challenging proof as well, too. So I'm going to make a couple parallel lines. So I'm going to extend from point X parallel to YZ out to a point W. I'll show you where W here is in a second. Then I'm going to extend Z outwards parallel to YX until it intersects that top dotted line. Where it intersects, I'm going to call that point W. So what did I make? Well, since I made both those red dotted lines parallel to the opposite sides, I made a parallelogram. So XWZY is a parallelogram. Cool. All right, where am I going with this? Well, I just stated before that if you have a parallelogram, we got the formula for area of it. So I got to do a little bit of work here, but watch what I do. But that's kind of the idea here is I'm going to take that area of the parallelogram and do something with it. I got two big triangles there. Let's see, I got triangle, let's see, XYZ and XWZ. Let's see if I can say something about them. So the next statement I wrote right there is opposite sides of the parallelogram are congruent. And I picked one angle, angle Y and angle W, to also say they're congruent. How do I know they're congruent? It's a parallelogram. Opposite angles of a parallelogram are congruent as well, too. Those are just properties of parallelograms. So that's congruent to that, that's congruent to that, and those two angles right there, Y and W, are congruent. So if we think about the triangles, now we're talking about the big triangles there, YXZ and XWZ, they are now congruent by SAS. So the two triangles are congruent by SAS. Therefore, if the two triangles are congruent, then by postulate yesterday that I forget the one off the top of my head, but the postulate that stated that if two shapes are congruent, then their areas are congruent. So that means the area, the entire area there of the entire parallelogram is equal to the area of those two triangles. Kind of see where I'm going with this. That's postulate 19. And since the two triangles are congruent from the previous statement, then 2 times the area of any one of those triangles will be equal to the area of that parallelogram. That's postulate 18. And now I'm just simply going to throw in the fact that I know the area of a parallelogram, that's the XWZY, is equal to base times height. So the base of that parallelogram is YZ. The height is H. I'm just substituting for that word area parallelogram. And then to get to the final answer, all I'm going to do is simply divide both sides by 2. So if I divide both sides by 2, I get that bottom statement right there, and I proved it. Area of a parallelogram, or area of a triangle, is equal to 1/2 base times height. And there you go. That's theorem 11.3. Most people, when they type it into a calculator, do base times height divided by 2. All right, just remember the base could be any one of the sides of the triangle, but then the height is that perpendicular distance between the base and the opposite vertex. My line there isn't drawn perfectly. You can see it's off just a little bit for that H. Should go right through the vertex. Okay. Once again, an 8th grade example of area of a triangle is pretty straightforward, but we're going to get a more high school level example of this. All right, so it says calculate the area. It's obviously a triangle. It's got 3 sides. I need base times height divided by 2. Clearly from the picture, the 2 sides are equal, so it's isosceles. We know that area of a triangle is base times height divided by 2. I know the base is 6, so 6 divided by 2 is 3, so 3 times h. I just don't know what the h is. So if I drop a perpendicular down from the vertex, that would be my height. And let's see if we can figure what that is. And not a special right triangle because I don't know what the angles are, but I do know from a previous theorem that if I have an isosceles triangle and I drop a perpendicular down from that vertex that's between the two congruent sides, that it cuts the base in half. So that means that side's 3 and the other side is 3. Now it's a right triangle, so I can find the height by using the Pythagorean theorem. So all I got to do is say that the hypotenuse, which is 8, square it, is equal to the square or the sum of the squares of the two legs of the right triangle. And that would be 3 squared plus the one that we're trying to solve for, the red dotted line there, and that's 8 squared. So just do a little bit of math here. 64 and 9, subtract 9, take the square root of both sides. Any perfect squares in 55? Nope. So h is equal to the square root of 55. Toss that back into our formula for h. 6 divided by 2 is 3. So final answer, 3 root 55 square units. That was a pretty good one. Remember, Chris, if you have any questions, make sure you send me an email. All right. One more time, same thing. Drop the it's equilateral this time. Drop perpendicular down, same drill. 6 divided by 2 is 3. Pythagorean theorem for the base is 6. Pythagorean theorem for the height. Oh, this one's 3069 because it's an equilateral triangle. You could use either technique. So I'll show you this one with special right triangles. So I know that if all the sides are the same, it's a 30, 60, 90 triangle. Remember, for 30, 60, 90, the short leg is equal to 3. The hypotenuse is equal to double A. So if A is 3, then the hypotenuse would be 6. And then finally, the height would be A root 3. So we know that A is 3. Therefore, the red dotted line there, the one that we want, the height would be 3 root 3. Cool. All right. We could also, what I'm showing you here right here, we could also do the same thing with the Pythagorean theorem, and you get exactly the same answer. 9 times 3 is 27. Square root of 9 is 3, so we get 3 root 3. So either one of those techniques that are on the left or the right side of the paper right here would work. Some people would argue that special right triangles would be quicker, and Pythagorean theorem is pretty quick too. And remember, you can only use the special right triangles when it's either a 30, 60, 90 or a 45, 45, 90. Pythagorean theorem is much more useful. All right, so take 3 root 3, toss it in. 6 times 3 is 18. 18 divided by 2 is 9. So we get 9 root 3 square units. All right, last shape of the day, and this will be your first new formula. We have a rhombus. Remember, a rhombus is kind of, well, it is a quadrilateral with 4 congruent sides. So squares are rhombi. The difference is in the traditional, and this is a traditional shape of a rhombus, is the angles aren't 90, right? Although a rhombus could have 90-degree angles. Most of the time we see a rhombus diamond-shaped, it looks like this. Okay. And so new formula, I'm going to prove to you that if you make the two diagonals of a rhombus and you multiply them together and you divide it by 2, you get the area of the rhombus. All right, so there's lots of ways to prove this. I'll show you one way. Clearly, we have a lot of triangles there. I'm going to look at a few of them. Immediately, I'm going to say that ADC, so that's the big triangle on the upper left, is congruent to the lower big triangle ABC. Now, why can I say that? Well, let's see, a rhombus has 4 congruent sides. So that means that AD and DC are also congruent to AB and BC. So I have 2 congruent sides, and I guess we could say the AC reflexive property, and that would give me an SSS. So those 2 triangles are congruent. Now what? Okay, so we know the formula for area of a triangle is 1/2 base times height. So I'm just going to pick one of those triangles, ADC. So 1/2 times the base. The base, I'm talking the blue line right there. So D1 for diagonal 1. Times, wait, it doesn't say times the height. It says half of D2. Why half of D2? All right, we got to remember, this is way back many chapters ago, that the diagonals of a rhombus bisect each other. So D2 would go all the way from D to B, but I only want half of that. And so that's why it says half of D2. Because remember, area of a triangle is 1/2 base times the height. And the height there would be half of D2. Okay. Well, I got 2 halves there. So if I move that half out or strip the half to the inside, I get a quarter. Half times a half is a quarter. Okay, where am I going to go from there? Well, Well, that was the area of ADC. Now, we just said that those two triangles are congruent, ADC and ABC. So for the whole shape, I got two of them. So if that's ADC, then if I were to double it, and that's what I'm saying right there, the whole thing is equal to those two add together. And since they're equal to each other, double that. So double 1/4 D1 times D2, right? And therefore you would get to a half D1 times D2. That's a pretty slick proof right there. All right, so that's our last theorem of the day. And it's the formula for area of a rhombus. Type it into a calculator once again. Most people do D1 times D2 divided by 2. Diagonals are, remember, the distance between any two non-consecutive or opposite vertices. Okay. Oh, by the way, area of a rhombus is also a parallelogram. So it's also equal to base times height. But if you don't know any one of the sides and all you know are the diagonals, then we would use one of those formulas there in yellow. If you know a base and a height, right, then certainly it's still a parallelogram, so you can use that as well too. So technically, the book doesn't show this, by the way. So technically, there's two formulas for area of a rhombus. Use whichever one makes sense. And that'll finish it for today. Some of the problems here, notice that shape right there is a bit more complicated. We simply need to break it up into parts that we understand to get the areas right there. This is more what homework looks like there. You got rhombi, you got triangles, and you have parallelograms to find the areas. And that'll do it for today. So good luck with your homework. If you have any questions, send me an email. And if not, well, I'll see you in the next day's class.